In this presentation, I'll be explaining three-phase half-wave control rectifiers. Coming to three-phase half-wave control rectifier, also called three-pulse converter, and three-phase half-wave control rectifier with a resistive load, say three-pulse converter with a resistive load. And this is the circuit topology, in which here, just to mark that, there is a primary delta connected primary, three-phase supply is given, A, B, C, and secondary is a star connected, and to that one three thyristors are connected like TA, TB and TC, and the load is connected to this meeting point, to the load, resistive load is connected between this point as well as the neutral point of this. Therefore this is a three-phase half-wave control rectifier circuit topology. Now continuing the three-phase half-wave control rectifier circuit diagram, already we have seen the last slide. Here it says delta connected primary and star connected secondary, and three thyristors TA, TB and TC in series to these three phases. TA, TB and TC, the thyristors are connected and shortened together, and there we connecting the resistive load between that point as well as the neutral point. So this is the circuit diagram. Now the thyristors with the most positive anode voltage will conduct if firing pulse. If you are giving the firing pulse, the thyristors having the max out of these three phases, phase A, phase B and phase C, which is having a maximum positive value, that will be conducting. Therefore the thyristor with the most positive anode voltage will conduct if the firing pulse is given. And TA, TB and TC are turned on. Here TA, TB and TC are turned on here at after omega t equal to 30 degree, omega t equal to 150 degree and omega t equal to 270 degree respectively for TA, TB, TC. Now let us see this one. This is a three-phase supply here. This is the phase voltage of A, phase A, and this is phase B. That is phase B is 120 degree shifted from this phase A. Again phase C, that is again 120 degree shifted from the phase B. For phase A, phase B and phase C, the input voltage as, that is the voltage at point A, B and C with respect to the neutral point, that is shown here, VA, VB and VC. Now let us see that one. Here normally in a three phase here, the firing angle is measured from this point for phase A, from this point for phase B here, and from this point in phase C, or this point means that this is equal to 30 degree. For alpha is measured from 30 degree for phase A, and alpha is measured from this point, that is 150 degree from this, from this point alpha is measured, so 150 degree. And again for phase C, from this point, that is 270 degree. From this one alpha is measured for the phase C. That is a normal method of measuring the alpha here, and this is corresponding to the firing angle alpha equal to 30. Now corresponding to the firing angle equal to 30 here, see this from this point the firing angle, that alpha is equal to 30. Now we are firing because that is positive, and that instant which is the maximum positive, that will be fired. Therefore at this instant firing angle alpha, we can see that one, the phase A is positive, maximum positive out of the three. Therefore phase A, T1, TA is fired here, TA is fired here. Once TA is fired or TA conducts here, the voltage at this point with respect to the neutral is same as this voltage VA. Therefore at this point the output voltage is equal to VA. That continues until this point, because still that continues until the current going less than halting current. Therefore that continues until this point. And again at here, in the case of alpha equal to 30 degree, 30 degree comes from this for phase B, 30 degree at this point, that is from here it is again 30 degree. At this instant the SCR which is maximum positive is this actually TB here. Therefore TB can, this one, that is this can be fired here at this instant. Once this is fired here, of course the current through this one is 0, and when this is fired here, then the voltage at this point is same as the voltage VB here. Therefore here again at this point the voltage VB comes here. Again at this point, again the current through the corresponding thyristor reaches to 0 value, and current is reaching 0 value, and that gets turned off. And at this point again we can see that one, the thyristor T3 is fired because the VC is positive here. VC is positive and that is fired here. As this TC is positive and is fired here, the voltage at this point is equal to the phase C voltage. That is the phase C voltage from this point with respect to the neutral. Therefore, that is the phase voltage comes the C phase. So that will be repeating. Therefore, what this darkened one, no, this is the voltage that is coming. This is the shape of the voltage that is coming across the resistance corresponding to a firing angle equal to 30 degree. Now, if you are increasing 30 degree, if it is less than, also it continues same as that one. But for example, if alpha is more than 30, say example alpha equal to 60 degree, if the firing angle equal to 60 degree, for example here, from here 60 degree it is, again at this instant the thyristor T1 is most positive, that is getting fired, and that continues to conduct. And once that voltage is reducing to zero, here the current flowing through this one is reducing to zero, that gets turned off. Therefore, the current, this thyristor is getting turned off. But next thyristor TB, that is turning on only after 60 degree from this point. Only after 60 degree from this point. Therefore, that this instant that is fired. Therefore, until this point, from this to this point, there won't be any current flowing through the load, or that's called a discontinuity happens. Therefore, then the voltage here will become zero. None of the thyristor is conducting from this point to this point. Therefore, the voltage across the resistor equal to zero. Then at this point, you can see that one angle equal to now 60 degree. That case, the TB is, or this is more forward bias, and that is the max voltage is more here. Therefore, TB is for getting triggered here. Therefore, this voltage is same as the voltage at this point, that is B phase. Therefore, that again at 60 degree, that is B phase voltage. Again, the same thing happens as the current flowing through the thyristor TB is getting zero. Here, that gets turned off, and you can say that one next thyristor has not yet turned on also. Next thyristor is under, that will be turning on after 60 degree from this point. But then we can see that none of the thyristor is conducting from this point to this point. Therefore, the current flowing is zero, or you can say that voltage equal to zero between the across the load, that's equal to zero. The output voltage equal to zero here, or the current is zero, I mean discontinuity happens. Therefore, that is again the C phase is conducting. As the C phase conducts, here the voltage is equal to the voltage phase voltage of VC, or voltage of phase voltage VC with respect to the neutral. The same thing happens here. Again, that is getting turned off once current equal to zero, and then again repeating like this one. Therefore, this is the output waveform corresponding to a firing angle equal to 60. Therefore, in this case, there is a discontinuity happens. Normally, if firing angle equal to less than 30, there is no discontinuity of the current here. But if the firing angle is more than 30 degree, there are certain duration for which none of the thyristor will be conducting, and the current will become zero. Or discontinuity happens if the firing angle is more than 30 degree. Therefore, if firing angle is less than, the load current is continuous, and if the firing angle is more than 30 degree, load current is discontinuous. The firing angle alpha is measured from always from these instant, like from this one for A phase, from this one for B phase, and from this instant for the C phase. Now, continuing three-phase half-wave control rectifier, we have to see first, if firing angle is between 0 and 30, as I explained the last slide, if firing angle is less than 30 or alpha, in that case, continuous conduction happens. And if alpha is more than 30, discontinuous conduction happens. Now, we have to derive the equation for the average voltage across the load. That is, we have to find out what is the average voltage of this one. So in this case, for example, alpha equal to 30, this is the shape of the voltage. Now, in order to calculate the average voltage here, because in a one period or from 2 pi radians, we can have the three such waveforms are there. That is why we are multiplying with the 3, that is 3, and we are calculating, first we are integrating from alpha to, that is, this is integrated from alpha to this point. That is, here what is this point? Alpha to, that is, no, not alpha, here it is alpha, alpha is measured from this here, then alpha plus 30 comes. Therefore, this point is alpha plus 30, and this point is equal to alpha plus 150, because this is equal to 120, therefore alpha plus 150. Therefore, the average voltage of this single is equal to alpha 2 plus 30 plus alpha 2 150. Vm sin omega t is the average value of the single one. There are such three humps like this one, or peaks like this one, so that becomes 3 times of that one area, and that is distributed over 2 pi radians. Therefore, 3 by 2 pi integral alpha to alpha plus 30 to alpha plus 150 Vm sin omega t d omega t, or 3 by 2 pi Vm minus cos omega t alpha plus 30 alpha plus 150. instead negative, we can do one thing, that we make it as positive and change the limit of that one. You can make it plus cos omega t and change alpha plus 30 can be brought here and alpha plus 150 can be brought here. Therefore, applying that one, 3 by 2 pi into Vm here, cos alpha plus 30 minus cos alpha plus 150. Therefore, that can be written as 3 Vm by 2 pi cos alpha plus 30 equal to 90 minus 60. Cos alpha 90 plus 60 is a 150. Or it is equal to cos A can say that cos alpha plus 30 minus 60, cos alpha plus 90 plus 60, or cos A plus B and cos plus, it is equal to cos A minus B minus cos A plus B, like that. In that formula, if you write that, it is equal to 3 pi 2 pi into Vm 2 sine A sine B, that is sine alpha plus 90 into sine 60. Therefore, substituting here for sine 60 and sine alpha plus 90, will be getting, it is equal to 3 by 2 pi Vm 2 cos alpha, it is equal to here sine alpha plus 90. Therefore, 2 cos alpha into sine 60 root 3 by 2. Therefore, 2 cancels, through 3 root 3 divided by 2 pi into Vm cos alpha. Therefore, the average value of this voltage, if a firing angle is less than 30, less than or equal to 30, if the firing angle is less than or equal to 30, the average voltage or the DC voltage available across the resistance, half wave control or three phase half wave controlled rectifier, it is equal to 3 root 3 divided by 2 pi into Vm into cos alpha. In terms of line voltage, we can write that 3 VML by pi cos alpha, because root 3 Vm is the line voltage. Actually, root 3 times phase voltage equal to line voltage, maximum value of the line voltage. For 3 VML divided by 2 pi into cos alpha, or 3 root 3 Vm divided by 3 root 3 Vm divided by 2 pi into cos alpha is the average DC voltage if alpha equal to less than or equal to 30. Now, if alpha is more than 30, as I already explained here, there's a discontinuity happens, because there will be zero current duration during which the output voltage equal to 0. And you can see that in order to find out the average value of this waveform here, you can say that again you can find out this area, and that is to be distributed. This area, there are such three peaks are there like this one, or they are to find out all this area and distribute over 2 pi. Therefore, it is equal to 3 by 2 pi for a discontinuous conduction when alpha equal to more than 30. For example, in this case 60 it is marked, 3 by 2 pi into Vm into, and here this is again V 3 by 2 pi into Vm sin omega t d omega t, and the limits are here, this is equal to 30 degree. Therefore, alpha plus 30 to pi only. So 180 degree only, because here discontinuity happens. For Vm sin omega t d omega t, or 3 by 2 pi Vm minus cos omega t alpha plus 30 to 180 degree. Just change the limits, change the limits here, then become positive. That is cos omega t cos alpha plus 30 minus cos 180. Or substituting here, we can get that 3 Vm by 2 pi into 1 plus cos alpha plus 30. Therefore, this is the equation for the average DC voltage if alpha is more than 30, and if alpha is less than or equal to 30, the average voltage equation in the case of a half wave controlled three phase rectifier, it is equal to 3 root 3 Vm by 2 pi into cos alpha. Therefore, as we have seen in the last slide here, in discontinuous conduction case, this is a discontinuous conduction is there are duration for which the current through the load is 0. None of the thyristor conducts, therefore the current will become 0. These durations, that's called discontinuity happens if alpha is more than 30 degree. And in that case, the corresponding equation for the average voltage, we have to write that one, that is equal to 3 by 2 pi into Vm into 1 plus cos alpha plus 30. That is for different alpha. For example, if alpha equal to say 45 degree, 3 by 2 pi Vm into 1 plus cos 45 plus 70, or cos 45 plus 30 or cos 75 happens. Therefore, thus that one, for different firing angles, you can find out what is the average DC voltage that is available at the output of this one. This is a three-phase half wave converter. That's it. Therefore, the drawback of three-phase half wave converter is that is it introduces DC component. If you see the current through this one, it is not pulsating. It does not have a positive and negative half. Therefore, what happens is that that will be saturating the core. The flux direction would not be changing. Always the flux direction will be in the same direction. So, it builds up so that it goes into saturation. Therefore, that's the one disadvantage of that drawback is that it introduces DC component in the supply current, which leads to saturation of the magnetic core of the transformer. That is, the DC component will be causing the magnetic core into saturation. It is also the relatively ripple factor is very poor because the DC content is very less compared to the ripple. Or ripple content is more compared to the DC component. That's VRRMS divided by VDC. That is called the ripple factor as such. For ripple content is more in that way. So ripple factor is very poor in the case of a half wave converter, three-phase half wave converter. That is why in the next we will be seeing full wave converter. Next presentation.